Welcome back. This is Mr. Greenstein's Geometry, and we're in Chapter 3, Section 3, Proofs with Parallel Lines. So the converse of the parallel line theorem are just as true as the theorems themselves. So the first one we had in the last section was the corresponding angles theorem, and it talked about parallel lines cut by a transversal. If we have that, then the pairs of corresponding angles are going to be congruent. But let's look at the converse of the corresponding angles theorem. The converse says that we don't know if these lines are parallel, but we do know that we have two coplanar lines that are cut by a transversal, and the angles 1 and 5 are congruent. If that's all true, then we know that these lines have to be parallel. So the way that we could phrase it is, if two coplanar lines are cut by a transversal and the pairs of corresponding angles are congruent, then the lines are parallel. We can also write the converse of the alternate interior angles theorem. Here we have two lines cut by a transversal, but we don't know if the lines are parallel. But we do know that the alternate interior angles are congruent. 3 and 5 are congruent. If we know that, then we know that the lines are parallel. So the way that we would phrase it is, if two coplanar lines are cut by a transversal and the pairs of alternate interior angles are congruent, then the lines are parallel. So it always starts out, if two coplanar lines are cut by a transversal and some pair of angles are congruent, then the lines are parallel. So that's a formula that we're going to use. We're going to use it for the alternate exterior angles theorem. So you could say that if we have two coplanar lines cut by a transversal and the alternate exterior angles are congruent, then the lines are parallel. We'll do the same thing with the same side interior, except that in this case, instead of saying that the angles are congruent, we're going to say the angles are supplementary. So I'll have you write those two out yourself, and then we will continue. Let's look at a problem. Let's compute the value of x that makes these two lines parallel. So to make these two lines parallel, then we have to make, these are corresponding angles, we have to make them equal to each other. And when you do, then you can compute x. And I'll leave it to you to compute what x is. For number 2, is there enough evidence to conclude that m and n are parallel? We have this 75 degrees and we have 105 degrees, and we have two coplanar lines cut by a transversal. Think about this for a moment. The answer is yes, we do have enough information, because 75 degrees and this angle on the other side here are supplementary, and that supplementary angle is 105. This angle and this angle are corresponding angles, and they're both congruent. Therefore, we can conclude that m and n are parallel. Now let's prove that we have parallel lines P and Q. So P and Q, we want to show that they're parallel. What we're given is that R and S are parallel to each other, and that angle 1 and angle 3 are congruent. So let's start out with the given. The first thing we know is R is parallel to S, and that angle 1 is congruent to angle 3. The second thing that we know is that angle 1 is going to be congruent to angle 2. And the reason why is because we have parallel lines, and these are corresponding angles, so it's the corresponding angles theorem. Now we can put together the fact that we have 1 congruent to 2 and 1 congruent to 3, so now we can say that 2 and 3 are congruent to each other. So angle 2 is congruent to angle 3 because we have the transitive property of congruence. And once we've shown that angle 2 and angle 3 are congruent to each other, we have two lines that are coplanar, P and Q. We have alternate interior angles that are congruent, therefore P and Q must be parallel. So we can say that P is parallel to Q because of the converse of the alternate interior angles theorem. So that's how we would prove P is parallel to Q. There's one more thing. There is a transitive property of parallel lines theorem, and it says that if P is parallel to Q and Q is parallel to R, then P is parallel to R. It's plain to see that P and Q have to be coplanar, Q and R have to be coplanar, therefore P and R have to be coplanar, and they also have to be parallel to each other. We will continue this discussion the next day in class.